Hello, my name is Professor Rad, and this is Precalc video 223, Properties of Logarithmic Functions. In our last video, we were graphing exponential functions, and we decided to try and graph the inverse since exponential functions are one-to-one. And so we saw what the inverse of an exponential function looked like, and we kind of previewed that those things were going to be called logarithms. So let's define what a logarithm is, and then because exponential functions and logarithmic functions are inverses of each other, we're going to use the properties of exponential functions to help us come up with some properties of logarithmic functions. So let's get started. So for our definition, we're going to use that inverse as our inspiration. So if I have an exponential function, f of x equals a to the x, then its inverse is the logarithmic function, f inverse is log base a of x. So just like the a is the base in the exponential expression, the a is the base in the logarithmic expression as well. In other words, log base a of x equals y means a to the y equals x. Now, you want to make sure that you're remembering this relationship and you're remembering the three components, the a, the x, and the y, and how they all work together. For whatever reason, my teacher who first taught me logarithms hammered into my head that a logarithm is an exponent, a logarithm is an exponent, the logarithm is the exponent. And so I remember that the logarithm equals the exponent. So notice that the logarithm equaling y is the exponent in the exponential expression. Then your base is the same, and then x fits where the other thing goes. I also remember this in kind of a cyclical manner. I think I start here with the base and I think a to the y equals x. So if I'm writing from a logarithmic expression into an exponential expression, that's the motion that I use. And if I want to go backwards, then log base a of x equals y. So it's that same circular motion. Here's my base. So log base a of x equals y. Log base a of x equals y. So that's how you can write from one form into the other. We'll be spending a little bit more time on evaluating logarithmic expressions in the future, but right now, because I had these properties on the board already, I figured why not just go through the properties first. So remember that a logarithmic and an exponential function are inverses of each other, which means the roles of x and y swap places. So for example, in an exponential function, the domain is all real numbers and the range is from 0 to infinity, not including 0. So when we look at its inverse, the domain of the inverse is the range of the original function. So the domain of a logarithmic function is going to go from 0 to infinity, and its range is going to be the same as the domain of the f of x. So the range is going to be all real numbers. Similarly, the roles of the x-intercept and the y-intercept are going to be swapped. So an exponential function has a y-intercept of 0, 1. So if we switch the x and y, that turns into an x-intercept of 1, 0. Then exponential functions have no x-intercept. They don't ever cross the x-axis, which means our logarithmic functions aren't ever going to cross the y-axis. So there is no y-intercept. Okay, then if we think about the graphs that we had before, we graphed 3 to the x, which looked something like this, very rough sketch here. And then we graphed log base 3 of x. So we took that function and we switched the x's and y's reflected over y equals x, and we ended up with something like this. So if we had a base for an exponential expression where a was greater than 1, we were an increasing exponential function. When we look at its inverse, this is also an increasing exponential function, or logarithmic function now, sorry. So that means if a is greater than 1, y is still increasing. So f of x is increasing. And if a is less than 1, we're going to have the same relationship here. it's going to be decreasing for logarithmic functions as well. Next, in our exponential properties, we were stating essentially our horizontal asymptote here, so that y went to 0 as x went to -infinity for a greater than 1. So now, remember, we're switching the roles of x and y. So this is saying that x is going to get close to 0 as y goes to -infinity. So if we look at what's happening here, y is going to -infinity, and the x value is getting closer and closer to 0. So if a is greater than 1, then we're going to say f of x gets close to -infinity as x gets close to 0. Now, we are going to also put a little plus sign here to the right of the 0 to indicate that our logarithmic function is approaching 0 from the right. This is because there's nothing happening on the left. So we're only approaching an x value of 0 from one direction. Then, similar situation here, if a is less than 1, we had y goes to 0 as x goes to +infinity. So now we'll have x goes to 0, and then y will go close to +infinity. So if a is less than 1, then y, or f of x, is going to approach +infinity as x approaches 0, again from the right. And another way you can think of us approaching only from the right is that our domain starts at 0. Well, it starts just to the right of 0. So we can't approach 0 from the left, only from the right. All right, cool beans. So we had a couple of points that were on every exponential function. So for inverses, you switch the x and y, and that'll give us 2 points that's on every logarithmic function. So it's going to pass through the point a1, and instead of -1, 1 over a, -1. Then, because exponential functions are smooth and continuous, their inverses will be as well. So logarithmic functions are smooth and continuous. And lastly, because we were able to find the inverse, it's still going to pass the horizontal line test. So logarithmic functions are also 1-to-1. All righty, so that's our full list of properties for logarithmic functions, and we'll apply these properties to help us graph logarithmic functions in the future, and to, to solve equations and things like that. I would like to do one example that builds on the domain, because remember, we were creating a list of things to look out for when you find a domain. So when we're looking for domains in general, remember, we're checking that a denominator is not equal to 0. And then if we have an even root, so if I have an even root, then the radicand has to be greater than or equal to 0. The stuff inside has to be bigger than or equal to 0. Well, now, because we have a logarithmic function, has a domain that starts at 0 and goes to infinity, we have to keep that into consideration as well. So now, if we have a log base a of some stuff, then that stuff has to be strictly greater than 0. So not greater than or equal to, and not just not equal to. It's got to be greater than 0. So 3 things we've now got in our domain as things to check. If we don't have any of these problem spots, then it's just going to be all real numbers. So let's do an example of finding a domain of a logarithmic function. Alrighty, so we're going to do 2 domains for this example. First, we're going to find the domain of log base 3 of 4x minus 16. And then we'll do the domain of g of x, which is log with a base of 1/2 of x plus 1 over x minus 3. So let's start out with part A. To find the domain of a logarithmic function, you need to make sure that the stuff inside the logarithm is strictly greater than 0. So we're going to set up 4x minus 16 is strictly greater than 0. Now this is a linear inequality because the exponent on the x is a 1. So we can solve this just like we would a normal equation. Just be careful if you multiply or divide by negative, reverse the sign of the inequality. So I'm going to add 16 to both sides to get 4x is greater than 16. And then I can divide both sides by positive 4 to get x is greater than 4. This means that the domain of our function is going to start at 4 and go to infinity. There we go. So that's the domain of this first function. Let's find the domain of the second one. So we'll approach it in much the same way. We have to take the stuff that's on the inside and make it greater than 0. So we have x plus 1 over x minus 3 is greater than 0. Now, you should also be keeping in the back of your mind that x can't be 3 either, because that would cause an issue with the denominator. So we'll bear that in mind. But now we have a nonlinear inequality. So let's focus on that first. When you have a nonlinear inequality, remember you want to get everything on one side, 0 on the other. So we're awesome, we're there already. Then we need to find our critical values and make a table of signs. So the critical values come from the numerator and the denominator if you set them equal to 0. So in this case, x plus 1, if that were equal to 0, we would get -1. That's a critical value. And if we set the denominator equal to 0, x minus 3 equals 0, then x equaling 3 would be a critical value. So on my table of signs, I need one spot for -1. I'm going to put a dot there because that is my x-intercept for this rational function. And for 3, I'm going to put a dotted line there because remember that's where our asymptote is going to come from. Then we pick numbers and we substitute them in to see whether we have positives or negatives. So if I pick 0 here and throw that in, I get a positive over a negative. So that will be negative. Now I need to pick something less than -1. So let's say -2. That will give me a negative over a negative, which is positive. And if I pick something like, I don't know, 5, that'll give me positive over positive, which is positive. All right, so now we write our interval for this inequality here. So we want strictly greater than 0. So even though we have an x-intercept at -1 for this function, we don't want to include the -1 because this is not an or equals to. So we're going to start out with -infinity up to -1, but not including it. And then we're going to union on. And here's where the denominator of the fraction part is going to be built into finding this inequality with the rational expression. Because in this rational expression, x can't be 3 anyways, so we would not be including the 3 anyways. So we're going to start out at 3, and we go up to infinity. So there we go. That's our domain for g of x. So we don't want to forget things about nonlinear inequalities because they are going to show up. They're going to continue showing up as we hunt for domains of logarithmic functions. So that's going to wrap it up for this video. We kind of had this nice relationship between exponential and logarithmic functions and the inverse relationship between the two. In the next video, we're going to start talking a little bit more about the logarithmic notation and how do you evaluate these things? Because like we can figure out like 3 squared pretty easily, but if I had log base 3 of 9, how am I going to know that that's 2? So how do I know how to evaluate logarithmic expressions? So I'm looking forward to seeing you in the next video. In the meantime, I hope you have a wonderful day, and I'll see you next time. Bye for now.